Okay. So hello everyone. My name is Martin. Today I'm here with Ivan and Tasso. Hello Ivan. Hello Tasso.
Hello, it's good to be here.
We are the maintainers of this project called ApolloAndroid. I just put here the Slack channel for our talk. If you want to ask questions, you can ask them in the Slack channel. You can also ask them on Zoom. We'll try to answer. This is a nice thing, being 3 speakers, is that we can answer the Slack and the Zoom chat at the same time. So hopefully that will work well. But today we're here to talk about ApolloAndroid and how we made ApolloAndroid actually work on iOS and even JavaScript thanks to Kotlin Multiplatform. A few words of intro for those of you who don't know GraphQL. GraphQL, you can think of it as a better REST. So instead of having to go to a REST endpoint and getting a huge JSON with a lot of stuff, that some of it you care and some of it you don't really care about, with GraphQL, you can just query the fields that you want and you will get a response with only the data that you ask for. So this is the nice thing about GraphQL. The other nice thing is that it's a complete type language. So it's completely fully typed. And it allows to do a lot of nice things like tooling, which ApolloAndroid does. So the fact that all your queries are type allows you to do stuff like generating models, Kotlin models that will represent your queries. So at a very high level, ApolloAndroid works like this. It takes queries on one side, your GraphQL schema on the other side, a bits of configuration, puts all that in the compiler, and in the end, you end up with generated Kotlin models. There's a lot of machinery behind all that. Part of it is what we call the core, which is mostly the compiler, a few API files to use on the device to declare some data structures used at runtime, and a Gradle plugin. So this is all already multi-platform, working on Android, iOS, and even JavaScript. And on top of that, there is what we call the runtime, which contains a lot of stuff to handle cache, transport, and a lot of things for executor, scheduling, and so on. So this is the final picture, but how we went to this picture, I'm going to leave the room to Tasso to explain us the journey to that final state.
Yeah, oops. Come on, cool. So yeah, so basically this is our timeline. We started more than 1 year ago in July 2019 with the initial GitHub issue. Of course, at that time, the whole library, whole project was in Java. Only the compiler code generation was in Kotlin, which is kind of separate already. Yeah, the first thing was to add the Kotlin dependency. It's the very first thing you can do. Right after that, actually, the first Kotlin Multiplatform plugin edition was not so far from that. I guess at that month it is winter time. We have nothing else to do, so it was a lot of work, very done quickly. Anyway, but adding multi-platform was easy, but especially actually converting that to multi-platform with a very basic release took some time, which we released to 2.0 version. With Kotlin multi-platform models. So basically what Martin showed just now. And a little bit later, we introduced Kotlin multi-platform subscriptions. Here we have the Android Summit timeline in the middle. That means like we are actually currently working on the new runtime that supports Kotlin Multiplatform completely, and with caching support, which is really important feature for Apollo as well. So we actually, the reason that it took a while in the beginning, we actually tried a couple of approaches. So I think I had nothing else to do at one point, and I completely converted everything using auto conversion in IntelliJ to Kotlin. Of course, this was a huge pull request where you cannot really even verify that it was working fine, but it gave us an interesting idea how we would approach this in the future, but we actually didn't merge this. Later, Ivan worked on it. So another approach we tried to do is to introduce Apollo API JVM module. So Apollo is a pretty complex project. We have a lot of modules already. Here, we wanted to separate JVM only functionality into a separate module so that the rest can be Kotlin Multiplatform. But the nice thing is that we figured out the Kotlin Multiplatform supports this already. So we will see in the future, soon, that you don't have to create a separate module. Actually, you can still keep JVM functionality in the same module, which is only shipped to JVM users. Pretty nice. So after that, what we did is that we tried an incremental approach, which totally worked much better. We were able to code review much better. So we sit down virtually and split the tasks and kind of do them one by one. Yeah, most of them was converting to Kotlin, but one other task was also to update OKIO, because at that time OKIO was also supporting Kotlin. So after everything was converted to Kotlin, not everything actually, let's say 95%, it was time to add Kotlin Multiplatform. So it's actually pretty nice. The multi-platform support in Kotlin it was definitely experimental at that time, but Gradle plugin is pretty decent. It works actually. The Kotlin Gradle JVM Gradle plugin, the native one, multi-platform, they all share a lot of functionality. They share a lot of code internally as well. So the first step is to just change JVM to multi-platform and keep the Java library. In this case, it's a simple Java library. If it is an Android library, you have to add the Android library plugin as well. Android multi-platform plugins are a little bit more complex. So in this example, we will look into Java example. So another thing you do is that instead of dependencies and other configurations in the Gradle file, you put almost everything in this Kotlin block. So you open the Kotlin block and then you define your platforms that you support. So in this case, we are just adding the multi-platform plugin by keeping the functionality the same, right? At this point, we are not introducing Kotlin native or JavaScript yet. So it is just JVM, and adding this with Java also allows you to still compile Java code in there, which is only available to JVM, of course, but it gives you this flexibility. And what you do other than like next is to define source sets. So this common main is the source set that is common to every platform by the name suggests. So it is a special one. In Kotlin multi-platform plugin, by the way, you define the dependencies inside the source sets. So you would have dependencies for the common, dependencies for JVM, maybe for Apple as well. Interestingly, here you can only define Kotlin only modules, right? So here we are only adding the Kotlin dependency and nothing else. Later we will have OKIO. And we have the JVM main source set where we depend on common main and define JVM dependencies. This is just moving the dependencies here. And interestingly, you also need to define JVM test. Instead of test implementation, you use regular implementation here, but they magically become test dependencies. So this is kind of like the conversion. It is a lot different, but it is easy. With this, you keep your library actually 100% backward compatible for the JVM users. So it's good to be incremental, actually. So it's this is good because you don't disrupt the code base. 100% backward compatible for the existing user. And at this point, you already support like a Kotlin Multiplatform plugin. So you could move Kotlin code one by one to the common module, right? So, but that's not that easy. So common module cannot have any JVM dependency at all. So it is not a simple move. So you have to remove those JVM dependencies. So there is in IntelliJ, there is this really cool feature. You basically right click a folder or a module. Here in this case, the example is the Apollo API module. We right click, analyze, and click analyze dependencies. When you do this, yeah, here you see the module is clicked. There are a bunch of features, but the default is pretty much fine. And here you directly dive into the dependencies. So Apollo API module, we started with that because we didn't have any internal other library dependency. This was the Leaf module. So it only have dependencies to third-party libraries. Like in this case, it is the Kotlin standard library, of course, available in multi-platform. We have OKIO. Thankfully, at that point, OKIO was also supporting multi-platform. So this part is pretty easy. But if you have any third-party dependencies, they have to support multi-platform. Next is you open the Java standard library, right? So of course you are depending on it. We have to check one by one and get rid of them. The first one is the IO package. So we do some file upload. So we depend on files. So that was refactored into supporting like file paths instead of the file class from Java. IO exception is interesting. There is a type alias to IO exception in OKIO. We directly started using it. And the rest was actually also pretty easy for things like closable. We had to do expect actual and type aliasing them into JVM implementation so that we can reference them in the common module. We will see a little bit of that soon. And the next big one is the big decimal. Actually, this is an interesting one. So we support big decimal for custom number types in GraphQL. So let's have a look how we did it. Kotlin Multiplatform comes with this expect keyword. So basically the API that you need to use, you define it just like an interface. You expect these declarations to be available basically. This is in common main and this has no implementation. In JVM, what you do is that you need to define the actual implementation. Actually, what is good about Kotlin Multiplatform is that it forces you to have these implementations in all platforms. It comes with, of course, IntelliJ support, so that tooling is pretty nice. But in such examples, it is pretty easy to connect to JVM main. You just type alias to the real big decimal, and that works fine. And on like one gotcha is we find out thanks to our unit tests is that we were not extending the number class. And some implementation were depending on the number. They were not checking instance of big decimal, but rather number. So we needed to do that also in here. The iOS implementation is more detailed. You have to provide implementation for every function, but we are delegating to the NS decimal number class that is available in iOS, like Apple Foundation, and that's pretty straightforward also. And another one is you usually have Java util class dependencies, array list, hash map, etc. You just delete the import and it's fine, because Kotlin doesn't need imports for them. During the conversion, the imports just stuck there, but you don't need them, you just remove. But if you are using things like concurrent hash map, those classes are now not available. You would have trouble using them in multi-platform. One thing that I want to mention is a Kotlin Gotcha. We had trouble with this for a really long time. So for our users, everything works fine after the library is compiled. But during our development, especially in Java classes, you would have such ridiculous errors. For example, it says this class is not extending throwable, but it does. So a couple of solutions we found to this is that either you convert this class to Kotlin. So we had a pretty big project. Now we are doing that. But if you have Java, this doesn't work. Or another way Martin found out is that even if you don't use Kotlin Multiplatform, you add Kotlin Multiplatform Gradle plugin, and then it starts working. And that's backward compatible. So it's fine. We opened an JetBrains bug for this too, but I think it's gonna take a while until this is fixed. So the next one, I will skip that because of time constraint. The next one is tests, pretty interesting actually. Kotlin Multiplatform provides you the ability to run tests once, but it runs it for every platform, JVM, JavaScript, Apple. So that's pretty good. But what we did is that, do you need to keep the tests in Java, or do you need to convert them to Kotlin? So first, actually, you need to keep them in Java because they are valuable. They also test your backward compatibility. That Java code is a user of your library already. So if you keep those tests 100%, that's already a proof of your library being backward compatible. So we kept them in Java first. We converted the whole library to Kotlin by not converting tests, but then we had to convert them because we needed to test our Kotlin native and Kotlin native implementation, right? So after keeping that for a while, we converted the tests to Kotlin as well, which actually revealed some bugs in our native implementation. Yeah, next step was the sample application. You spend so many time on a library, and it is usually the last thought to add a sample, but I think we did a good job at the end. The library is pretty good. It uses coroutines as well, even from the beginning, and basically all kind of business logic. It's very simple GitHub client, lives in the KMP lib sample module, and then Android application and the iOS application are just building the UI. They don't have any logic at all. So it just connects to the repository available in the library, and that connects to Apollo to make the GraphQL requests. And also we have iOS library that is contributed by Alan Shapiro from the iOS Apollo iOS team. So that is also pretty decent, and it also uses Swift UI. So it is pretty modern. Now I will hand over to Martin to talk about the publication, because it's also very complex.
Sorry, I was muted. So yes, once we have all this library working multi-platform, we still want to publish it. I mean, we want users to use it. And for that, it's usually better if you publish it somewhere. So if you have published JVM library at some point, you might have seen this. So this is the typical layout of a Maven repo with one big jar file containing the Java code, the Java bytecode, one for the sources that IntelliJ can download so that you can inspect and navigate easily. One for the Java doc, which I'm not sure what it's there for, but some platform mandate it, so we put it there. And the POM file, which describes the module as well as the dependencies. When it comes to multi-platform, things are way a bit more complex. Because you have so many platforms, like JVM is one, but you also have iOS for the simulator and also for the real devices. You have JavaScript, you might have Windows, Linux, watchOS. Well, that's a lot of stuff. If you go back to the JVM artifact, you will see it's mostly the same thing. There's one difference is that now you have a module file, which is a new thing from Gradle, that I will cover a little bit later. For iOS simulator and ARM, you now have Calib artifacts, which are like jars more or less, but for native binaries. And then for JavaScript, you also have a jar file, which is completely different from the JVM one, because this one contains JavaScript, well, obviously. There's also one module that is called metadata that is containing a lot of information about the types and the structures you have in your library that cannot be represented in different languages and different platforms. So for an example, null safety is not really a thing in Java bytecode. So if you ship Java bytecode, you still need to know let know IntelliJ that sometimes are nullable and sometimes are not. So this is done through this module that contains a lot of metadata about the library. And last but not least, you have this common module. So if you're doing multi-platform, you might have seen it sometimes suffixed with -common or something like this. And this module actually contains nothing but the POM file and the module file. So if we open the module file, this is called the Gradle metadata, not to be mixed with the Kotlin metadata. There's a lot of metadata there, but the module file is what's referred to as Gradle metadata, and it allows to reference all your platforms from a single Maven module. So if you look inside, you have all your different platforms, and you can think of it a little bit as symlinks. If you deep dive a little bit, like the iOS API variant will link to the iOS ARM64 module for the iOS real devices. And if you have done that in the past, like declaring artifacts and modules Maven dependencies for each and every source set, well, this is not the case anymore. And actually JetBrains starting doing that by default with Kotlin 1.4. You can now use a single Maven coordinate and Gradle will look up all the different platforms for you. The nice thing is that even if you don't use the multi-platform module, it's still working. So you just have to remember to use this common module and it should work out. This is all doable thanks to the Maven Publish plugin. So if you're looking into publishing, you can find a lot of different ways to publish, like the Bintray plugin. You also have a legacy Maven plugin. There's a lot of solutions. If there's just one takeaway from this section is that you should really use Maven Publish. It's really easy to use and it creates everything with a good layout. And you can, of course, publish on Bintray and gcenter with Maven Publish. It's just another repository to add to your Gradle files. I have one last slide that I'm not going to talk too much about it because mainly Russell covered that a little bit earlier. And also because I have really no idea how this works, but this is the next thing when it comes to multi-platform project and publishing even more metadata. So this is coming next in ApolloAndroid in a future version. So that was for publishing. And now I will leave the room back to Ivan to talk a bit more in detail about code generation and the future of the library.
Cool, thank you, Martin. So yeah, let's return back to the, oops. Yeah, let's return back to our code generator. So just to give you a recap, what the code generation is basically we call it compiler, and so we take some configurations, and as we are generating type safe models, so we obviously take the schema and we take the query. So we validate the query against the schema. So we parse, build some IR, building some AST, and actually at the end, we actually generate the models, Kotlin models. And so to simplify that is basically you have a GraphQL query, and for that GraphQL query, we are generating a model that represents that query, and also it generates a model that represents a response for that query. So as you can see, we are generating a data, and we're generating a hero that contains the type safe and nullable safe fields that you requested, so ID and name. So this is a JVM version of the generated Kotlin model. So what it actually took us to make these changes to our code generation and make it generate the actually Kotlin native models. As you can see, this is actually the model that you can consume in Kotlin native projects and Kotlin multi-platform projects. So as you can see, it's the same as a JVM, and so we were lucky here because the first is that, first of all, that all our models that we generated is, they are dependent on the API files, or you call it supporting files. And we easily migrated all our supporting files to the Kotlin native. Also, we are only using the pure language, Kotlin language, so we don't have anything like from JVM land when we're generating the Kotlin models. And the only extra dependency that we have is the OKIO to actually parse the response from the stream. And the only one that we actually just was easy to replace is we were using the IO exception from JVM. We replaced this with the OKIO. So again, thanks to the OKIO, starting from the 2.3.0, it works with the Kotlin native, so we really didn't have to do anything. So I just, we'll have a lot of supporting files and API files. So with that, we migrated to the Kotlin native. It was very straightforward, but I want to point out this JSON reader and writer. So basically, when you send the GraphQL query, you get the response, and response is represented by the JSON. And because we are generating a model that actually knows how to parse this JSON, we need the JSON reader and writer. We need some JSON engine that will just read and write the JSON. So we took the implementation from AOSP, the same implementation for the JSON reader that I believe Moshe is using. We migrated to the Kotlin and make it platform agnostic. So, and that's allow us to actually take the stream from OKIO and have this JSON reader to actually parse it and parse it into the models that we actually generated. So with the CodeGen, we were lucky, not much work, but with Apollo runtime was a different story. Just to give you a context what the Apollo runtime is. First of all, it's responsible for the networking, and we are using the HTTP or WebSockets. Also, we have like 2 different cache. First is based on it's basically HTTP request response cache, and we're using dscalar cache as a storage. We have also normalized cache that we are either store in memory, or we basically on Android we are using the SQLite. I will also want to point that we supporting the GraphQL subscriptions that is using the WebSockets, and it's used Apollo GraphQL WC protocol. So this is the context of what the runtime is. And when we start assessment, like how are we going to migrate our existing runtime into the Kotlin native, this is a key point that we start discussing and concerning actually points. So the number one point is obviously that it was written in Java, but more importantly, it was actually designed and thinking in Java. We are using in some places, JVM concurrency constructs like atomic operations, thread pool executors. Obviously, for the Android normalized cache, we are using SQLite. HTTP client is used for our network transport layer, also for subscriptions, and also for the HTTP request response cache. We have like external dependency for the New York Times store that we are using for our normalized cache that in memory. And so this is like a key points of the runtime existing, and we start evaluating like, okay, what that means. So written in Java, fine. We can just like convert the Java to Kotlin and suddenly it should work. Then like JVM concurrency, okay, fine. We can probably replace with the Kotlin native some concurrency construct, like maybe Stanley, use the Stanley library for that. SQLite, it's totally fine because we have SQLite that is a multi-platform library. The first one was that some kind of a showstopper for us is the HTTP client that we are using for a network transport layer, and it's not Kotlin native yet. New York Times store library that we are using for in-memory cache, again, it's written in Java. We could convert that to Kotlin, make it platform agnostic, but also it's deprecated. So, but all of this doesn't really matter because of this. When we start looking into the deep, how we're going to migrate that to the Kotlin native, we actually, we found that we are missing the proper layer of abstraction in the runtime. And by that, what I mean by that is basically, one example is our HTTP models, they actually leaked into our business logic in our a query execution. And also we are using the HTTP models for our HTTP cache and so on. So basically, the key point here is that you cannot just take the Java project, convert everything to Kotlin, replace bunch of dependency, and suddenly it's going to work. No, you need to introduce the proper layer of abstraction. And after all of this, we decided that, okay, maybe it's probably will take the same effort as we are going to write the runtime from the scratch, like a new runtime. And when we started approaching this problem, so basically the key points was this for us. First of all, the runtime should be Kotlin Multiplatform library from day one. So, and we were targeting JVM and iOS and Android from day one. The big decision that we made is that all our API is going to be represented by the coroutines. So coroutines is the first class citizen for our API. And this actually allowed us to have a nicer API, and also it provides us flexibility. One example is that with exposing as a flow, user can easily have the retry mechanism of your query depending on some different conditions. Also, another point that in existing runtime, we have some leaked abstractions. So basically, we have some API related to HTTP cache, even if you are not using the HTTP cache. So we wanted to set up environment where HTTP cache or normalized cache is absolutely pluggable and optional. The next is bigger one is that we want to abstract completely our network transport layer. It should be platform agnostic, and it should be transparent for the request execution. By doing all of this, like abstraction, we actually see potentially new way for our features. Like, for example, we can easily now serve the queries and mutation over the WebSockets. Or like, for example, we can easily add now the query batching execution when we batch the queries into one and send as a one request. This is our very high level architecture, I would say, but just overview how we are thinking about like the new Apollo runtime. So on the left, you have Apollo client. This is an entry point to the library. In the middle, you have request execution, and each feature, each like new feature is actually represented by the interceptor. So it's a bunch of the. So basically, we are constructing a pipe with a bunch of the interceptors, and each interceptor is performing some job. So for example, we have a bearer token interceptor that will track, if you get the full one, we actually will try to renew the token and to try the sending again the network call. Also, like we are thinking that any new feature, like for example, the HTTP request response cache or normalized cache can be implemented as the intercepted and pluggable into this chain of interceptors. On the right, we have the network transport layer. It's the completely abstraction that allows us to actually perform some network calls. And you can notice that till this moment, everything that I am currently described is a common. There is zero platform specific code. And only the small portion of that is related to the network transport that like it's actually platform specific. So Apollo provides a default implementation for the HTTP and WebSocket network transport layer. We are targeting iOS and JVM and obviously Android. But because we have this nice abstraction of network transport, you can easily provide your own implementation, like for example, Keter network transport, or for test, we can provide the mock version of network transport. And by abstraction, what I really mean is just again high level of the overview what the network transport is, but basically it's just interface that it gets the GraphQL request and returns a flow of the GraphQL response. And obviously, we don't want users all the time to write own implementation of network transport for different platforms. So we're providing default implementation. And in this case, we have Apollo HTTP network transport that implements this network transport. And on iOS, it's working through the new NSURL session. On JVM, it's based on OKHTTP client. The same for the WebSocket. Again, like on the iOS, it uses the NSURL session. On JVM, it's used the OKHTTP client. So if you notice that like on this previous slide, but what I want to point out is that there is actually two powerful mechanics how you can introduce dependency on the platform. The one mechanic is using the GI. So basically you injecting implementation into the object. So in our case, when you construct Apollo client, we injecting the implementation of the network transport. And because it's just abstraction, it's just interface. So for from the code point of view, Apollo client doesn't care what kind of platform it's working on. But at the same time, we are providing default implementation of this network transport. And here we're using expect and actual. So basically what it tells that the user can expect that there is a default implementation for the network transport, that actual implementation network transport for both iOS and JVM. So this is very powerful. And yeah, so this is, we just started working on that, like not just started on runtime, but we need to add the new features like a normalized cache, a request response cache, but we have already running a sample app. We have the already new Kotlin runtime that you can try. Simple Up is actually iOS application that uses this runtime and the code generation on iOS. And we have this master ticket that we are trying to keep updated with the new PRs that coming in. Yeah, so that's basically it for today. And we believe that Kotlin Native has a bright future. And this is our really small contribution to the Kotlin Native libraries. And yeah, thank you so much for your time.
Thank you, guys. Did you want to do Q&A here? I see. Well, you've been responding to questions. It's great. We can carry that over to the Slack channel. Anybody have questions they'd like to throw in the chat that we can address now? No? Okay then, guys. You came literally right down to the wire. It's great. I'm going to stop recording now.